In this video we'll be looking at a harder circuit than the more simple circuits we did towards the beginning of the course. So I'm going to rub out the title to give myself plenty of space to draw a circuit. Okay, so we'll start with the power supply, and we're going to make that a 6-volt cell. And we're going to add to the circuit a 2 ohm resistor, and we will continue and we will add a couple of resistors in series, and then we shall return that back again to the start. And what we'll do, we'll have this resistor here as 4 ohms and this resistor here as 2 ohms. So it's a more complicated circuit now. And a question could be, I'm going to say, what is the current, let's call it current I3, what is the current I3 passing through the 2 ohm resistor? Okay, now let's think about the first way to approach it. When approaching a problem that involves series circuits and parallel circuits, the first thing we must always do is to reduce the circuit so that we have simple series circuits. So we're going to work out the combined resistance of the parallel resistors, and then from there on we shall continue in our calculations. Now, first of all, we can add some labels if we want. We know that there's a current I1 passing through there, and conservation of charge, we'll get I1 returning there, I3 passing through there, we've got current I2 passing through the 4 ohm resistor. So these are our currents. Now, in all these questions, we'll be using the formula V equals IR, which calculates the relationship between current and resistance. We'll also be using the fact that for parallel resistors, 1 over the total resistance is equal to 1 over one of the resistors plus 1 over the other resistor plus etc, etc. Now, we've only got 2 resistors, so we can stop there. So the first step is I'm going to calculate what the combined resistance of those 2 resistors are. So 1 over the resistance is equal to 1 over 4 plus 1 over 2 equals 3/4. We flip it, so therefore the total resistance combined to the parallel is equals R equals 4 over 3, and that's equal to 1.33 ohms. I'm going to take it to 3 significant figures so that we can be accurate in our answer. Okay, so that's the first case. So now we know what the total resistance there is. Now, if we wanted to find out what the total resistance in the whole circuit is, we'll add the resistance of that resistor to the resistance of that resistor. So what we'll find is the total resistance in the circuit, let's call it R total, is equal to 2 plus 1.33, and that is equal to 3.33 ohms. Okay. Now, the reason I wanted to find out what the total resistance was, so then I could apply this equation here, V equals IR. We know what the potential drop across the whole circuit is, which is 6 volts. And we now know what the total resistance is, so from there we can work out the total current. So I shall rub away my working and continue. So, we have from here, this equation here, we will get that current I, total current going through, or if you like, I1, is equal to voltage over resistance, total 6 volts over 3.33 ohms, and that comes out as 1.80 amps. So the total current going around our circuit is equal to 1.80 amps. Now, if we know the total current going through the circuit there, we must know the total current going through this particular resistor here. So if we know the current going through that resistor there and we know the resistance, we can calculate the potential drop across it. And then once we find the potential drop across there, we can use it for later calculations. So if you like, we'll call that the potential drop V1 across this resistor. And I will draw, okay, so that's V1 there. So if we put a voltmeter across there, V1, the potential drop across there, V1 is simply equal to IR, which is equal to 1.8 times by 2, which is equal to 3.6 volts. Okay, fantastic. So we now know the potential drop across there. And of course, we know the potential drop across there. If we know the total potential drop across the circuit is 6 volts, we can then find out what the potential drop across those parallel resistors are. Okay, so I'll continue and I shall rub up the working. Right, so we know that V1, the potential drop across that resistor, is equal to 3.6 volts. Now, the potential drop across both those resistors there are going to be exactly the same as each other. Okay, it's because because there's nowhere, if you imagine it drops to there, so it goes from 6 volts there, and it drops 3.6 volts, so therefore 6 minus 3.6 is equal to 2.4 volts. So therefore, there must be a potential here of 2.4 volts. And then across here, goes back to 0 again, the potential must be 0 volts. So we must be dropping 2.4 volts across each resistor. So, if I continue, we'll find that, okay, now, the 2.4 volts across there, and we've got 2 ohms there, well, we've got 2 out of 3, so we can find our current. So I3 must be equal to V over R. V over R, which is equal to 2.4 divided by 2. Okay, and 2.4 divided by 2 is simply equal to 1.2 amps. So we now know that I3 is equal to 1.2 amps. And that was the answer to our question. And we could double check by making sure that the current going through there is equal to the current going through both there.